Hello everyone, we know that artificial intelligence is revolutionizing healthcare in many areas such as disease diagnosing with medical imaging, surgical robots, maximizing hospital efficiency, and so on. So let's dive right into the first project, which is regarding the image segmentation or the tumor segmentation over the brain MRI images, right? So here we have multiple images along with their corresponding mask, right? And we are going to visualize and verify the model prediction for the same, right? So we will be using deep learning and the transfer learning for the same. And after this video, you will know how to apply artificial intelligence to detect and localize brain tumors. That is great achievement in the healthcare project. Okay, so let's dive right into the first code we are going to establish here. Let's explain this code here, right? All right, so first, in the first step, we must understand the problem statement and the business case. What is the business case here, right? Here we can see the artificial intelligence market is again 45.2 billion USD, right? In by 2026 it will be, and current evaluation is 4.9 billion dollar USD, right? So for X-ray, MRI scans, we have multiple opportunities. We have so many opportunity there, right? So you can say that this task will be very, very useful for you, for your projects, for your uh, problem, right? So you can go ahead and you can ask for the simple statement, right? So in this case study, we are going to improve my, right? We are going to diagnose the segmentation part, right? Where we have multiple brain MRI scans, where we have tumor location, and along with this, you can see this white area is there, right? In this white area, you can see this portion is again uh, location of your tumor, right? You can have that MRI segmentation there, right? All right, so here we will be using we will be using this data source, right? So let's see where this data source is located. I'm going to open in the new tab. You can see this is asking my leave in Google Colab. So I'm going to see where this data set. You can see this is the downloadable data set, and I'm going to see one by one. Here you can see these are patients ID, and each patient ID is consisting of different images here, right? So you can directly download this file, right, from these 46 patients, right? Sorry, 46 files in a single patients. And if you go up, then you will find multiple patients having multiple patients ID, right? So what exactly they have, what is the data look like, right? If I had already downloaded this data set, I'm going to show this one folder here. Can you see correspondingly we have this image, right? If you look at the image here, so you have this image, and along with this image we have the segmented tumor value, right? Can you see this is the segmented tumor? For 0 it's showing the black, right? Or for 255 it's showing the white, right? Wherever we have this black portion, this pixel value will be 0, and this 255 will be white portion, right? Again for each, if you look at the naming part of these images, can you see this is ending with 601, this is 60120 mask, right? So respective mask is there after each images, right? If this image is, this mask is entirely black, which means this is the 0, this is consisting of 0 pixels everywhere, and we do not have any tumor in this image, respective image, right? So this was the one of the example. Apart from these folders, we have the dataset value and data mask CSV. We will be using this file again. So what is the purpose of this file? Look at this file. This first column consisting of patient ID. The second column is patient image path. Where is the image path, right? Can you see? Respective patient ID is having respective image path. And next is mask path. What is the location of my mask, right? Then we have 0 and 1. So can you see wherever we have 1, which means we have the mask at that portion, right? We have the tumor segmentation in that part, right? If we do not have any value, which means 0, so we can see this. Can you see this is the tumor portion, right? This is the categories as a tumor, right? So let's just start with the coding part first. So apart from this, we have the JSON format, other files. I'll be uploading all these files in my GitHub account. You can go in the comment section, right? Coming back to the coding part, right? If you want to see the AI medicals imagery, so you can see this is the another part, right, where we have MRI scan along with the brain tumor locations. Top companies, those are using MRIs. For free time, you can learn about these links. I'll be uploading all these files and all these links. I'll share all these links for the same, right? So let's understand the layered architecture, right? Here we have the input images. Here we have ResNet deep learning, and then when we have ResUnet segmentation model. So ResUnet segmentation is actually the combination of UNet plus residual block. So detection, it's going to detect tumor location on the pixel level. It's going to detect also healthy patient, which everyone would get this prediction. Yes. So the purpose of this study is to perform image segmentation here. So I would like to start by the goal of image segmentation, and we will understand extract information from this. We will be using CNN and fully convolutional network, deep neural network, and we are going to solve the current task, right? So what is the image segmentation? I'm not going to elaborate this theory because this session is about the coding part. I'm going to illustrate coding part more so that you can you can understand the concept, and this concept makes sense to you, right? Here you have this softmax function. We will using the softmax function, everything, right? So this was the end of the task 1, right? What is the task 2? So task 2 is to importing libraries and dataset, right? So I'm going to import so many libraries in my file so that we can use all these library. And here you can see we are using pandas for data set, right, for data frame processor, numpy for number operations. Then we have the Seaborn, Matplot for data visualization, CV2 for image processing, and so on. Other libraries are also there. The name itself explanatory. We have the learning rate, and we have the global, random, and we are going to collab import files. So in order to upload files to collab notebook, I'm going to use these library. I'm going to run this cell so that we will have all the libraries in our IPYNB file, right? That's it, right? Then we will have to mount our drive because everything I had uploaded in my drive, actually Google Drive. So there is a certain code to drive. So what is the code? So I'm going to write from google.collab. I'm going to write google.collab. I'm going to import drive, and from this Google Drive I'm going to mount here. So for this I'm going to write the drive.mount, and then I'm going to write the value where it will be mount, right? So I'm going to write content inside the drive, right? So you can see on the left hand side we have this files option, and if you see there is only simple sample data file is showing here, right? But I want to import other files. I want to mount my Google Drive. Whatever content will be there in my drive will be depicting here as well, right? So it's asking my permission for my Google Drive. Of course, that's the accessible, that not that should be very. So I'm going to assign this one, continue, right? So you can see the text on the screen. Here we have only sample data. Very soon we will have the drive option, right? So it will be showing all my drive content, right? Information regarding mounter and drive. You can click over here. This will be the, can you see, this is the Stack Overflow option where we have the Google Collaborative option, right? You will be finding each detail over here. Every detail is there, right? If you refresh this part on the left pane, you will find this drive option. Can you see under this drive, I have my drive option, and my drive will consist every folder, every file which I have in my drive. Actually, let me show that part as well. So here I'm having google.com. Here I'm having drive option. So if I'll show the drive, so can you see all these files are just imported there, right? I can see reflected part there, right? So this is the part here. So everything is stored in my folder brain MRI tumor, right? So I have this archive folder in this, and in this Kaggle 3M I have all the files of my patients. I had already uploaded. It will take time to upload in your drive, right? So make sure you had already uploaded all these files in your drive as well, right? And keep remember the name of your folder where you are uploading in your drive, right? So for example, if I'm going to search in my drive again, so for example, I'm going to search brain MRI tumor. So here you can see same archive folder is here. Inside this archive I have Kaggle M3. For me it took around 1 hour or 2 hours to upload all these files. Here you can see along with these patients images and masked files, I'm holding other files actually also. So other files like the JSON files or CSV files or the dot Python dot py file which we will using for the error purpose, right? We have the weighted files also, right? We will using all the files I had already uploaded here, right? I'm going to close this window. Here we have all the files. So next part is to navigate my drive directory, right? So why I'm going to navigate, because currently I'm pointing somewhere else, right? So I need to point my, actually this should be the location, right? So I'm going to write %cd. For this I'm going to locate this drive, right, where I'm holding all the respective folder. So I'm going to copy this path, and that's it. Just paste it in front of cd, %cd, just paste it, right? That will mount your directory. Right now your current location is this one. So everything you will be extracting or writing the path, you will be showing that value, right? So there's information syncing when we, once you have the correct option here, right? So we are almost here. So data containing this one. So we are going to show the path to brain MRI and their corresponding MRI. So for this I'm going to show, create the brain df and pd dot read underscore csv. Under the csv I'm going to have this data underscore mask. In this mask I'm having csv file. I'm just hitting this value, right? So what is the mask actually? So mask is the image segmented. To understand this portion you will have the pixel level value, right? We have this 00 means we do not have any mask. We have 255 means we have something white portion, right? Which is the you will be able to catch that part where this is consisting your mask actually, right? So if you want to see, if you want to find out the other portions, right, other detail, you will be write brain underscore df, then info operation, and then we will get the all the information. Can you see everything is there? Patient id, image path, mask path, and mask, right, which is in the integer format, right? So let's see what is the ingredient of this file. So we have the brain underscore df dot head. I'm going to show the first files. you can see the same ID, patient ID is showing here, image path is showing here, right? And then we have the mask path and we have the mask is equal to 0, right? Let's say we have the instead of head, if you want, I want to see the last 10 images, right? So I'll write tail and then 10 images, last 10 images will be depicting here, right? So I'm going to have this images here, right? Now, in the later part, we are going to mount the brain MRI image, right? How to write this image here. So I'm going to copy and paste this one, and this would be the brain MRI part, right? So can you see this is the brain MRI part task, and here we have the all the sections, right? Next, what is the path to image segmentation? Of course, this would be the image path, right? I'm going to display the image path. Can you see this is the image path? So this time I'm going to show the image path, right? Can you see it's showing the image path? But first challenge is, do we have balanced data set? How many samples are classified as healthy? This is the first challenge, right? So I'm going to obtain the number of images with the mask. So for this, I'm going to write the code for mask. I'm going to write the value to counts. For each category, we are going to show this values. For this, 0 where we do not have mask, 2556. For the mask images we have 1373 only. So the main points discussed here, we have imbalanced data set. But anyways, we are going to good to go because it's very hard to collect the tumor segmentation data set. So I'm not going to solve this problem. Rather, I'm going to move ahead with the same data set. But you must know your data set, the nature of your data set, right? So then we are going to perform in the task number 3, we are going to perform the data visualization where we have patient ID, image path, and everything is there. And then we have the respective 3929 rows and 4 columns. If you can figure it out, you can see there we have the uh, respective values for the same, right? All right. So in the next part, I'm going to find this one, the mask value and whatever the index, right? Whatever the index value is there, right? And now I'm going to show the interactive bar chart for each values, right? So for this 0 and 1, right? For these two categories, these two classes, I'm going to show the bar chart and their respective value. For this, I'll be using Plotly graph, Plotly library, and I'm having this code for my value counts. Can you see this value counts dot index will be this just pasted here, right? I'm going to use my figure for this bar chart. I'm going to use this classes, right? This classes number 0 to 1, right? This is just pasted here. Then for brain MRI, I'm going to use the brain fast dot value counts. For this, I'm having this value 0 and 1, this count number. And here we have the RGB. So 0 to 200 means green and 0 to 55 means dark green, right? So I'm going to display this chart where we have the 2026 and for 1 we have 1373. So this is the interactive color and we are going to define this color for the same, right? Let's see how we can see the image mask path, right? Here we have multiple image path, right? In a same fashion, I'm going to display the image path where we have all these library here, right? So this is the image path and this is the mask path, right? You have very crystal clear idea what is the location of this path, right? So let's show one by one what is the mask path here. So I'm going to write random number here. You can write any number here and display the mask value here. So for this take away from this part, you can see this is showing the mask value here, right? If this code makes sense to you, then you can see we are using CV2 and I am read function for this mask path. in order to understand, in order to read this value, these images one by one, right? Let's say can we display this respective image? Of course we can display. I'm going to display this part here, right? So this is the CV2 brain images 623. So respective image is just showing here. Can you see? This is the respective image, right? If you follow what I'm saying, you can understand the code. So try to understand this code. What is the meaning of this code, right? Do not just run the code and everywhere, right? If you want to see the respective value of this, so for 255, what is the value, right? What is the maximum value here? We have 255, and for 255 means white, which means there is a pixel which is consisting of this mask, right? When we are looking at the minimum value of this one, so in the same code I replace this maximum by minimum. So this is showing 0, which means we have the black portion as well. We have the 255 means we have tumor, we have white portion, we have black portion as well, right? Now, in the next step, I'm going to visualize the image, which is the MRI and mask, and the data set separately, right? For this, I'm going to import this library, right? For this importing, I'm going to import this subplot for 6 comma 2, 6 rows, 2 column, right? I'm going to display the 6 values here, right? 6 images. This is the reason I'm taking 6 rows here. For two sections, first one will be the MRI and second column will be for mask, right? And this is the image size, figure size for me, right? So for count is equal to, for each count I'm going to display this value. So this will be keep continuum on count number, right? For each range I'm going to, for each image 6 value, I'm going to define the random integer here till the length of the brain, right? So along with the length of the brain DF, so I'm going to pick up the random index number. It's going to pick up the random value, right? It's not every time if you run this cell you will get different output, right? Different layout will be depicting here. So I'm going to display part here. This will be visualize my images, and it will be very clear to you that you have so many images there along with their mask, right? And you can use this one. So it's taking 1 or 2 minutes. So of course it will be taking. Here it is. Can you see? We have the brain MRI and mask. Brain MRI and mask. Can you see? Mask 0 means we do not have any segmented here, right? 1, 2, 3, 4, 5, 6. Can you see? Mask 0 is also here, right? If I run the same cell again, so I'll get different layout, different images with respect to the MRI images. If you remember the images and their respective mask, you will feel, analyze that this time we are going to display different set of MRI, and this will be the main idea, and you will pick up on the main idea where we will have random images on the screen. Just because of this code random.rand integer in between 0 to length brain df, we are getting this MRI images. Can you see? Now we are having different images. First one is image mask, first one is image 0. Can you see? Here we have multiple masks and multiple images, right? So what is the next challenge? Next challenge is to plot 12 random numbers selected MRI images, and we are going to visualize MRI scans along with their mask on the image. So I'm going to display these images. The code will be same, but only few changes will be there, right? So here is the code. I'm going to display this code, right? So this code will be there for the 12. This time we are going to display 12 images, right? Corresponding mask, both MRI and corresponding images, right? This will be MRI, this will be mask, MRI with mask, right? So can you see this is showing only the mask images? Can you see this condition? This is the equal to 1. So it will be showing the images, respective images, which will have mask only, right? So we do not have any images which is not consisting any mask, right? So you can figure it out like in the previous piece of code we had some images, those were not having any mask, any segmentation, right? But here we also having some not any not segmentation here, right? But in this code you will get every code, every full, every images which is having segmented. Can you see the mask is showing here, MRI with mask, right? Mask is showing here, MRI is mask. Why this red portion is showing here? Can you see this one? This is the red color. Whatever the image color is, this one, this is the mask equal to 255, and this is the RGB. So this is the reason this is showing 255000, right? Let's change this 255 to, let's say, I'm going to make it 255, right? So what is the meaning of 255 RGB? This time this will be something, I perceive this will be green this time, right? So you can change colors as well according to your sense, right? You can catch the sense of it. What is the value of this number? What is the meaning of these numbers, right? How RGB concept is correlated with this red color concept, right? So it's taking much time. So very soon we are going to display. Can you see now everything is going to display with the green color? Can you see these green colors are showing with the respective mask images, right? So this is the concept behind the color of operations, right? Okay, so now let's understand the theory and intuition behind the convolution and ResNet. Here you can see this is the neural network concept, and we are going to perform the everything. So this is the last layer where we are going to tumor detected or tumor not detected, right? So first we are going to diagnose whether this image is having any tumor portion or not, right? Then you can manage to get the point where we are having. So how to perform this feature extraction and convolution, right? So I'm going to display this one, right? So this is the explanation part of this one, where we have image kernels. Here you can see everything, every image is just showing the respective image value. Can you see every image is just scattered in a converted in a numerical value in between 0 to 55. If you have this one, right, if you have 0 everywhere, so that is the black, right? Can you see if it is very black, so it's around, the number is 20, which is approaching to 0. If this number is white, which means the number is approaching to 255, right? The concept makes sense to you. Here we have the sharpening. For example, we have the blur image. I'm going to blur image. So can you see this is going to perform the kernel size, and every kernel is going to convert into the blurry image, right? This is the input image and this is the segmented or the output image, corresponding entry of the values, right? So this is the video. Here you can see you can up and down your kernel values, and there here you will get the output images, right? So I'm going to share this link as well, right? Now go ahead for the ResNet network. Here we have the different architecture. I'm not going to detail or illustrate this portion because this is the theory part and this section is not the theory part at all. So if you want to read the more about this this paper, you can, this ResNet network, you can see the deep resonant learning for image recognition. Here you can see the 50s here. By increasing the layers, it's not guaranteed that your training error will be improved. Here you can see by increasing 56 layers, the training error is still increasing. Here we have even 20 layers, the training error is lesser than 56 layers, right? In a same fashion, we can see in the testing error, for 56 layer, respective error is higher than the 20 layer model, right? So this paper is all about the number of layers you can keep in your network, right? This paper is all about the architecture. Here we have the residual. Here you can see all these arrows are showing the jump or the residual network, where we have we are following gradient descendant problem, right? So I'm not going to explain this gradient descent problem. What is the gradient descent problem? Where when we have n number of layers in our object, right? So how to solve this residual vanishing gradient problem is here. So this problem occurs when the gradient is propagated to earlier layers, right? Which results in a very small gradient. So this is the solution for the same problem, right? So I'm going to move ahead for this. So again, this ResNet is working upon ImageNet dataset, right? We will be uploading this ImageNet dataset, of course, right? So this is the theoretical part. You need to extract the theory, and this is not the coding actually. So you need to explore the CNN architecture and their performance compared from this site, right? If you look at this one, Control F, I'm going to ImageNet, right? Can you see this is going to ImageNet classification, right? Everything is just written here, right? You just go there through this paper, you will find the okay. So what's our next task? To understand the theory and the intuition behind the transfer learning, right? Here we have transfer learning so that we do not have to perform the task which is being reused every time, right? For as a starting point for another similar task, we are going to train the weights, train the neurons, right? And this is widely used since we started from the pre-trained network model can dramatically reduce the computational time required if training is performed from scratch, right? So this is the image network, and using the image network we are using the weights for this model, and finally we are taking our new images, right? And we are going to change this last dense layer, right? And this dense layer will be trained on a specific task, right? For example, we need to classify cats and dogs, right? African elephants and everything. For image network we have the train model, right? So this image net having very large scales, right? And very large image network, so we are not going to image, right? If you want to see the transfer learning, this is very good resource here. So I am going to just give the reference for the same, so that you have plenty of time and you can summarize what we have learned in this session, right? So if you go down, scroll down, you will find comprehensive hands-on for guide, transfer learning, for deep learning, for the image learning part, where we have image learning challenge, right? 1000 object classes, we have 1000 classes here, and then we are going to traditional ML and transfer learning, difference between, right? And it's already actually saving our time, right? So many hours are being saved here. If you can catch the sense of this one, you will find the concept of this one. Here is the introduction to transfer learning for deep learning. Very good example, very good theory here. We have the concept, detailed concept here, right? I'm going to move ahead with the list of challenges transfer learning, right? What kind of challenges we are going to face it. This is again the theoretical part. This is just homework for you, and you can just go ahead for this part. Now, in the task number 6, I'm going to train a classifier model to detect if tumor exists or not, right? So what is the tumor? So here we have the brain tumor. I'm going to drop the patient ID, which is the least used, right? Because patient ID is not playing any important role to diagnose my images or to segmented my path, right? Now I'm going to convert every mask images into the category format. Why? If you will not do this, if you will not convert this column, you will get this error. If you comment this line, you can get this error, and you will have to convert every mass column into the categorical column. Right, here it is. Right, if you want to see the output of your updated file, you can see here it is the updated file. This is the information regarding this one. All right, can you see? This is everything is in the data format. Everything is in the object or the data categories format, right? Now, here you can see you can divide in the next part. You will have to divide the data set into the training and testing part, right? So for test size means 50% 15% data set is going with the train testing, and rest 85% data set is going for the training part, right? So I'm going to split it here, and then I'm going to perform the pre-processing part for my Keras API, right? If you do not have Keras pre-processing API, you will have to install in your segmentation, right? I'm going to install this part here, right? Then I'm going to use this file in order to create an image generator, right? So for this image, this file, I'm going to use this image generator, right? And then using this data generator, I'm going to scale the data from 0 to 1 and makes validation split into the 15% and 85% respectively, right? So here is the image generator for rescale, which is going to rescale every pixel which is in the format of 255 into the 0 to 1, right? Then I'm going to train the generator and going to split the file into the train, validation, and the testing part. So this first part is going to train. This is going to create that sub part. This is the training folder, and inside this training folder, I'm going to use the class model, right? So this will be the train target size 256 and 256, right? In the same fashion, I'll be creating my validation path where I'm going to use the validation path, right? I'm going to paste this code where I'll be creating my image path, all the folders, all the images, which will be creating a data generator for my validation. And now finally, I'm going to create the test generator for the same, right? Here is the test generator, right? So I'm going to run this file so that I can have three different folders for the same. Can you see? Entire files, every folder, all the images are segregated into three portions. First one is the validated, and then is the uh, training, testing, and validation part, right? So you can connect the dots here that we are dividing each value, and then we are going to create validation, training, validation, and testing folder here, right? Now I'm going to create the base model for the same, right? So what is the base model? So base model is the ResNet 50. I'm going to ResNet 50 weights. For this, I'm going to use the ImageNet dataset, ImageNet weights. Include top means I'm not going to use this one, right? So I'm not going to use the dense layer at the end. I don't want to include dense layer at the end, right? This is the reason I'm going to keep it false. So tensor input, my input size will be this one. 3 is what? Why? Because the channel is 3, right? RGB channel is there. This is the reason I'm going to keep it 3 here, right? So this is going to download my value, and everything is going to download here. So these weights are openly available, right? This is the open source weights, and anyone can download here, right? If you can go here, you see this is the downloadable file, right? I'm going to stop it here, process, right? Once we have the data model or the base model for my ResNet 50, right, then we have the base model here, right? I'm going to display the base model here, right? So can you see this is the base model, right? This is the base model summary. Now, if you want to freeze the model weights, so this is the model weight. I'm going to use the model weight here. So I'm going to freeze the initial models for which we are not going to train, right? For which we are using our custom model. So for this, I'm going to classify my base model. I'm going to include this one, right? So this will be the including model, right? Finally, I'm going to use the training summary. This would be the training summary value, right? All right. So this was the summary of my base model here. You can see this is the summary, and here we have n number of parameters, right? And this is this is taking so much memory. And here we can see we want to freeze the model layers, right? Model weights, so that we do not want to train our models, right? All the layers, all the initial layers, we are going to use the predefined models here, right? And then you want to add the classification head of the base model, right? For this you will be using multiple terms, multiple multiple activation functions, multiple flatten layer, right? For this, can you see this head model? First we are going to use 2D 4x1, and then we are going to flatten. Then we are going to use ReLU activation function. You can use any other functions, but I'm going to use ReLU activation function. You can uncomment these two lines so that you can play around with this one, right? You can pick up on the main idea why we are adding all these functions, why we are. So finally we are using softmax for our binary classification, right? These layers are just added in my model, right? And if you look at the model summary, so here is the model dot summary. So this will display the updated model for you. Here you have the included these summary part, right? For this you had included the summary part, right? Now I'm going to further, in a further part, I'm going to compile the model here, right? For this we have the categories, we have the optimizer Adam, we have the matrix as the accuracy, and I'm going to check the accuracy for the same, right? For this I'm going to use the early stopping, right? So early stopping for validation if loss is not decreasing even after certain epochs, right? So what is the epochs here? Can you see the patience is equal to 20? So even if 20 epoch, even after 20 epochs, if accuracy is not improving, then exit from this training part, right? I'm going to exit from this training part till this patience level is being achieved, right? So I'm not going to decrease my model. This is called early stopping, and this check is going to check my file classified ResNet weights. So where is the ResNet weight here? Make sure you have already uploaded all these files in your drive which you have mounted here. So in the brain MRI folder, archive, in the Kaggle 3M, if you look down, if you scroll down here, you will find all these weights which I had already uploaded here. Can you see? Everything is already uploaded here, right? Can you see? This is already uploaded here, right? So I'm going to just use all these blocks, right? So this was the early stoppage method, right? Then I'm going to use this part where we are going to train the model, right? So I'm going to use this part. For this we are going to validate, and for only epoch 1 I'm going to check the accuracy for my model. You can increase the accuracy if you need more, if you can increase the number of epochs here if you need more accuracy or less accuracy in your case, then you can provide inside in this code, right? I'm going to pause this video because this is going to take very long time here, right? All right, so meanwhile my model is going to fit this train generator. For only epoch 1 we are going to illustrate another code in this same fashion, right? So later on we are going to save the model for this for the future purpose, right? So I'm going to save the model here. So this would be the classify ResNet model JSON. So where is the location of this one, right? So where is the location? This location would be same folder Kaggle 3M. Can you see? If you scroll down, you will find this model file as well. Classifier ResNet model JSON. Can you see? This location is same, right? Classify ResNet model JSON. This is the JSON format where we will be leading this architecture. We will be storing the weights of this architecture, right? So once we have saved this model, then we have the uh, next challenge for this mini challenge, right? This is going to change, this is asking to change your network, or you can play with this network with respect to dense layer, neurons, or dropout, right? It's not mandatory that you are keeping the same architecture. You can change the same model, and you can print out the model summary and compare the trainable parameters between the original and the new model, right? So I'm going to add the classification head and the base model, and you will find this is going to show the respective respective layers as well. Here we have all the respective layers. So pool size is 44 comma, flatten layer, ReLU layer is there, dense layer is there, and other functions are also here. I'm not going to run this code because this code is already running here. Once it is we be completed 177 over 177, then only we will be able to run these piece of codes, right? Okay, let me illustrate the next task. So next task is to analyze the performance of my trained model, right? So with the ResNet 50 MRI, so again let me show you the location. What is the location of this ResNet 50 MRI JSON? So you will go down, you will see this is the location of my ResNet 50 MRI JSON format, right? So it will be extracting or importing the same model, same file, where we are going to able to load pre-trained model. Instead of training the model for 1 hour, more than 1 hour, we are going to utilize the pre-trained model here, right? And finally we can load the model. For this I'll be using the Keras API. So I'm going to use the model which is we have saved here, and then weights, we are using the same weights here, and for we are going to compile this matrix, right? Then finally we are going to make the prediction for the same. Again, it will take much time, so I'll have to wait for a couple of minutes, right? So this will be the generator, this will be 16, right? This generator will be divided by 16, and verbose is equal to 1, right? For this I'll have to wait again for around 10 to 15 minutes, right? Then you will have to check the test prediction. What is the text prediction here? That would be the leading part, right? You will have to check the final prediction size. What is the prediction size here, right? If you want to see the test predict, what is the test predictor model, you can go here, you can see what would be the ingredient part of this model, right? Then we can obtain the predicted class from the model prediction, what we are going to predict here. So I'm going to copy and write the code for this argument, for this prediction model, what we have predicted for the test predicted for all these files, right? Finally you can print this one, you can see this will be showing the model, right? So since we have used the test generator, it limited to images to length of predicted due to batch size, but you can see it's going to use the something else. So I'm going to use the original one. So what is the original one? So this is going to original my task test mask, right? So test mask will be there, will be utilized here in order to show the values, right? Then finally I'll display the accuracy here. I'm going to display the model accuracy, which will be the uh, 98, around 98.61, right? Or you can display the confusion matrix for the same, whatever the confusion matrix will be there, and false positive and true positive values that will be displayed over here, right? And eventually we will see you the final mini challenge, right? So mini challenge number 6 is expecting to print out the classification report and comment on the precision, recall, and FWS score, right? So how will you comment this one? I'm going to write this code. For this, I'm going to write this one is here. This is the code where we can write the code for my classification road. All right. So now the let's understand the theory and t-shirt with ResUnet, right? So ResUnet is actually segmented the mask, right? So this is going to divide into three parts. First one is the encoder, second one is the bottleneck. You can see this is the bottleneck and the decoder expensive path, right? This is the architecture here. So first contraction path is including encoder where we have all the necessary. Here you can see they have the color path like max pooling we are using here. For this gray one, crop and concatenation, right? Wherever this one is gray, where we have the crop and concatenation. The green ones are up and convolution layer 2 cross 2 1. Everywhere we have the convolution layer. And convolutional orange one is 1 cross 1, where we have this one. This portion is directing referencing here. Convolutional 3 is represented by purple one. Here we have the all these convolutional 3 cross 3 resolution ReLU network, right? The objective of this ResUnet architecture is to perform the segmentation path, right? Once it is having the tumor, then it is asking to segment it that part, right? This is used for bottleneck part, right? So for this, we have the different blocks that takes the input and then passes through the ResNet block followed by 2 cross 2 upsampling convolution layer, right? Then again, we had the ResNet architecture, encoder, bottleneck, and expanding the decoder part, right? You will including the architecture network, ResUnet network here, right? So additional resource for this, you will have to read the research papers if you want to understand deep dive regarding the ResUnet architecture. You can go and seek the basic theory here, right? Finally, we need to build a segmentation model to localize tumor, right? For this, I'll have to get the data frame containing the MRIs which have mass associated with this, right? So I need only the mass one. So I'll pasting this mask is equal to 1, which is having mask images, not the without mask, but only mask images are there. In the latter part, I'm going to divide the data set into the training and testing part, which we had done earlier as well. So I'm going to repeating the same task for my segmentation model. Previous was the classification model. This was the segmentation model, right? And later on, I'm going to create the separate list for my image ID and image part. And we are going to class ID to pass into the generator path, right? Here I'm going to use the utilization, which this file is containing the code, right? This code is having custom loss function, right? Whatever the custom data generator is here, right? So I had included this file as well. So this is the utility. The name of this file is utilities.py, right? Can you see this utility.py? If I open this file, you will find this will be consisting all these necessary custom accuracy, right? So this is the reason we have all these functions, right? So here we have the functions, right? So then we will have to create the, once we have the utility files contained overhead, then we have to create the ResNet blocks. So I'm going to use the custom code for this. So I'm going to use the function for this ResNet block where we have the respective code. So first one is the input file, second one is the kernel file, right? I'm going to he normal. So this is the activation, this is the custom activation, right? If you want to see the illustration part of this one, you can see these files, and these key normal activation is just explained here, right? So we do have conventional activation function, but rather I'm rather using the conventional ReLU or sigmoid or another activation function, I'm going to use this activation function. This is the custom activation function, right? For this code, the coding part of this E normal is just included here. Can you see? This is the understanding part of coding is ResNet, right? Here we have the 1752 layers, and this is having 3.57 classification top 5 error percentage, right? Others are having very high error, but this is including very less error. ResNet. So as compared to GoogleNet or VGG, LXNet, we have very less error comparison here, right? So I'm going to skip off this one. So here they have shown the classification of different portions, right? For example, we have the class for this one. We have the image for belonging to this image, this sign symbol. We have image for 1 2 3 4 5 and so on. Can you see the respective binary numbers? They are enabled in a same context. Now we have the notebook for the same. So the all these files, all the code is just inbuilt into the same code here, right? And finally, I'm going to write a function to upscale and concatenate the values which we have passed, right? So I'm going to include that function which we have written here, right? Right? And then I'm going to utilize, once we have created the upsample concatenation, now we can use the code for the input shape, right? This is the input shape, and there here we have letter stage 1 resonant block. If you go up, that this is the resonant block. So for the same res block function, we are going to use here everywhere, res block, res block, res block. It will call the function up and move down, up and move down. And later on we will be solving this mini challenge. We will print out the segmentation model and summary to find out the total number of trainable parameters, right? All right, so once we have saved the model and we have created all the layers for my model, so I'll have to print out the segmentation summary. So for this we have the model. This is not the conventional model. With this model is regarding segmentation, right? So I'm going to segment this part, right? And then finally I'm going to create the loss function where we have the utility file. So I had included this loss function in this utility files, right? If you want to see the more information regarding this custom loss function to train the ResUNet, so you have used the what we have used in this one. So you will go here. This is the text file. Can you see? This is the ResNet file. This is the confusion matrix. This is the TP or TN or Tversky, right? This is the everything we have imported here. Every file we are going to import here, right? This is going to use this model and backend file, right? So the same accuracy model, same accuracy term, same custom loss function, custom data generator I have included in this file, and this is the just here. So this is very good article published by author Abraham, Nabila and Khan. They have published their journal in this format in 2018. So I'm just using their model, right? Finally I'll have to compile this model again. It will take time, right? So I'll have to keep in the pause fashion so that I can train my model with the respective optimizer. I'm going to compile this model, right? And then again repeating the same, early stopping for the same model, right? Even this patient is going to here. So this patient is 20, right? So till 20 epochs, if my accuracy is not decreasing, this will perform early stopping, right? This is the meaning of patient is equal to 20, right? Right? So then I'll have to save the model in the architecture. So how would I save the model? I'll have to save the model here. So I'll keep the model here with the name of ResUNet model. So then eventually I'll have to check in the task number 11. I'll have to assess the train segmentation residue model performance, right? For this I'll have to load the architecture model. I'll have to use the predefined accuracy parameters here, right? Predefine custom model here, right? Custom trainable model, right? Whatever we have, the loss function we have used, what kind of custom data generator we are used, which is containing the code for the same. So I'm going to use all these performance model here. So this would be the task number 11 to assess the train segmentation residue node performance model, right? Then finally I'm going to use the utilities for the prediction part. So I'm going to use that part where we have all these stuff. I'm going to use this one and then going to create the segmentation part, right? I'm going to create the data frame for the result, right? For this I'll be using this part where we have used the we are converting this data frame. So this will create the first column by name image path, second column predicted path, and third column has mask, right? And we will creating this custom column, right? And then we will have to merge this column to the previous one. So what kind of data set we have, what kind of original data set we have, we are going to merge this column, right? So that we have the new model, right? So once we have this one, so we will have to display all these values, all these terms. We are going to at least 10 values, right? So 10 images I'm going to display here. So for this I'm going to display 10 images. So I'm going to plot all these 10 images. Can you see this is showing to 10 images and this is showing the 5. So why reason this is showing 5? First one will be the for brain MRI, second will be for original mask, third will be for AI predicted mask, then we will have MRI with original mask, ground truth, and fifth one we will have MRI with artificial intelligence predicted model. Can you see first, second, third, fourth, and fifth? So for all these fifth columns we have the fifth column. For all these 10 images, random 10 images, we have this one. And can you see this if condition? This condition is true, which means we are having the we are having only segmented images. We are not interested in the not segmented, the images those are not having any tumor in it. So we are going to illustrate or display only the images those are having segmentation, right? So corresponding mask, and we are going to display we're going to plot 10 images along with their corresponding mask and visualize, verify that model predictions made sense for us, right? As you can see that we had already trained the model for only epochs 1. It took around 1 hour for me. So it depends upon your hardware situations where we have different configuration. It may take lesser time for you. But as far as the saving model is concerned, it will take very less time. So we are going to save this architecture into the JSON file for further purpose, right? So this was the mini challenge. I had already pasted the code. I'm going to just run this model one by one very quickly. And we had seen the task number 7 in order to assess the train model performance. Here is the save model. This is going to use the saved model and checking the accuracy for the same. So here we have used the optimizer atom and accuracy parameter is matrix accuracy parameters, right? So then again I'm going to use this name, this test predicting for the test generator site, right? Once it is being predicted, so we can use the same variable for the further purpose, right? Here it is taking the around 5 to 10 minutes, right? Then it will be ready to use for you this one, right? So I'm going to pause this video again so that it will be compiled for all 36 steps, right? All right, so all my epochs are successfully trained, and then I can check the shape for this model. where we have the 76 rows and 2 columns, right? So I can check the test predicted values. How many columns do we have? We have the array values here, right? So for this, I'm going to use the predict for it in order to uh, predict class for the model prediction, right? If I want to display the predict value, you can see this is showing 0 1 0 1 1 1 and so on, right, for the respective classification, right? So since we have used the test generator, so it is limited to length predicted, so due to batch size, so I can obtain the accuracy for the same, right? So here is the 97.57 around, right? You can also create the confusion matrix for the same in order to check the accuracy. Can you see this accuracy for the 01 and 01 model, right? For 2 classes only. Here is the solution for the mini challenge, where we have the classification for these two classification report, right? Precision, recall, F1 score, support. You can go for the external resources in order to check the model, right? So we had the understand the theory behind this ResNet model, where we have the architecture, right? So I'm going to scroll down little bit and then going to check this value here. Now we are going to perform the segmentation model, where we have all the mask images and their associated mask, right? So we have 1373 images, those are masked, right? So I'm going to split the data set for the same, and right, so we are not going to consider those are not having segmented tumors, those images are not having tumors. So we are interested only tumor images only. So these images are just segmented into the 15 to 85 ratio, right? Here we are going to create the list for the same generator, and then finally I'm going to use the utilization, the code generator with the file which we had in the .py file, right? Then we have the residual model. So this function is just created for the reuse. This function is also using he normal activation function, not the conventional one. For the segmentation purpose, we are going to use the function for upscaling and concatenation the value. And then finally we are going to use this res block function in each layer. You can see convolutional layer is using this res block function. This is the customized function which we have used here, and we are going to use this res block uh, custom function everywhere, right? And then I had just run this code here, right? Once this code will be run, you have all the layers or updated layers are there with the relu and with the sigmoid function, right? And if you want to see the summary of this segmentation model, you will find all the summary, all the concatenation and all the activation functions are displayed here, right? And finally we have the loss function and their respective parameters, and then we have the we will have to compile the same, right? So I'm going to compile the same so that we will have the same accuracy, right? If you want to use the early stopping for this patient is equal to 20, you can run this code, and eventually I'm going to save the model. And once this model is saved, then I can use this model to check my performance here. So this is going to use my weights, predefined weights, and for my purpose, and I'm going to utilize this certain code for my custom loss function and custom generator values, right? So this will include the mask ID, mask and image protection, right? All right. So I had already stopped this one. You can run this code for very long time. So it's taking very long time. So I had just stopped it here in between. But that's not issue. You can run for very long time. In the later point, you can create data frame for the result. So for this image path, we will have the first column for this predicted image. For this, we have the has mask, right? So I'm going to merge from the original one, which is the df prediction, which is the previous path, previous file, and this will be the new file. So can you see this is consisting now 1 2 3 4 5. So 5 columns are there where we have the all the predicted mask and everything, right? So then we have the count, so where we will have all these count value, and I'm going to display the count for 10 images here, right? So the 10 images will be displayed for plotting the corresponding mask, and they are going to visualize their model prediction that is going to make sense for you, right? So 5 columns will be there. For one is for brain MRI, second is for original mask, then AI predicted mask, then MRI with original mask, right? So these 5 images will be there for the respective code, right? So here you can see this would be the output of the code, right? Can you see? This will be the code, when this would be the output, which will consist brain MRI, brain original mask, AI predicted mask. Like my model has predicted this segmented part, right? Pixel level segmented. This is the MRI with ground truth, right? MRI with predicted mask, right? This one is mounted with this one. This image is mask image is mounted with this one. So output of this plus this is fourth column. Output of this third plus one is the fifth column, right? So this is the reason we are getting this output here. Okay, so this was the mini challenge, and this mini challenge is there that you need to create the 30 images for their corresponding mask, and finally visualize, verify the model performance, right? Now you know how to apply artificial intelligence to detect and localize brain tumors, right? This was a great achievement in healthcare, right? Can you see? This is showing all these predicted masks, right? If you want to see the first one, you can see this is just showing all the respected values, right? So if you want to see the respected find out, so you will find out the final images here. This was the all about the image segmentation. I hope you find this video very informative. I hope you will like and subscribe this video and spread and forward to your needy one. Thank you so much.